Hey everyone, this is the next topic we are covering in memory management, and this is the topic after virtual memory OS policies. There will be many important topics in this video. You can check them out in the description below. So let's begin. Okay, so to handle virtual memory, operating system needs to employ some policies. Okay, so what are they? Like the fetching policy, the placement policy, replacement, resident set management, cleaning, and load control. What are all these we will be seeing in this video and the next video. Okay, so first one is the fetch policy. Fetch policy determines when a page should be brought in the main memory. Okay, so as we all know, all the pages, all the processes are not in the main memory at one time. Okay, so there should be some policy, some algo, or some system to determine when to brought a page into the main memory. Okay, so there are two ways this is done. One is demand paging and other is pre-paging. Okay. So in demand paging, the page is brought when a reference to it is made. See, it is brought when there is a location or there is some part of it which is required by the program. Okay, the process. The process requires something and it is in a page. It is brought in at that time. So in the start when the memory is all empty and we employ this demand paging. So in the start, the filling of the memory, there are many page faults. Okay, each time a page is brought in, there is a page fault. Okay, but later, as the memory got filled and we have seen the principle of locality, the faults reduce and the references we made then will be among those which we have already loaded before. So this principle of locality and demand is based on the fact that we can predict the future if we analyze the past. Okay, so if this thing happened in the past, these pages were in demand in the past, they will be in demand in the future. So that's how demand paging works. The next topic is pre-paging. Okay, what pre-paging is? In demand paging, we looked at the past, and in pre-paging, we try to load pages which are not referenced yet. It's like we are future planning with this. It is use of the fact, it makes use like if we are going to get something from the secondary memory, why don't we get it in a bunch? So it would be better than to bring again and again small pieces of memory. IO operations since takes lots of time, so it would be such a bother to go every time and fetch a page. Okay, so in this pages are, it also makes use of the fact that in secondary memory the pages are stored nearby continuously. So instead of loading a page at a time when it is referenced, it loads a bunch of them. Many nearby pages it loads at one time. So that's the fetch policy. Now the placement policy. Well, placement policy decides where it is placed. Okay, where it is placed in the main memory. See, in pure segmentation method, it is actually a very important aspect to look into where it is placed because that's why we employ various algos like the best fit and the worst best fit, first fit, because it helps to manage and get free space later on. So it actually matters where it is placed. Only in some of the schemes, like one is segmentation. But in paging it's not much of a significance as the sizes are fixed, so anything can be placed anywhere. It doesn't matter where it is placed. And on a side note, it is an area of research in non-uniform memory access processors where there is a shared memory between many processors, and it actually matters a lot whether the memory is close to some processor or not. Okay, so how much data a process has in its nearest locations. Okay. Another policy is the replacement policy. See, we have seen fetch, we have seen placement. So now, when the memory gets full, there is a need for replacement. Okay. So the policy which decides which page to replace when a new page is fetched. Okay. So the objective is that we have to really think about it, ki which page to replace. So the best thing would be replacing something which we are not going to be used in the future, in the nearby future, okay, which will be referenced very late in the future. Okay. So as complicates the so as much as complicated the replacement policy gets, the sophisticated it more sophisticated and overhead is required to implement such a policy. Okay. So yeah, regarding replacement, there's one more thing we should consider is frame locking. So what is frame locking? It's a frame which is locked. Okay, as simple as that. So there are many kernel processes and other OS or critical areas which are locked and are not available for replacement. And they are usually denoted with the frame bit, that is the lock bit, which is 1. So yeah, there are some frames which are locked and not available for replacement. So now we need to replace the pages. So there are many algorithms we follow, and we are going to discuss 4 of them. One is optimal, second least recently used, third is first in first out, and the fourth is the clock policy. Okay. So what is the optimal policy? See, it replaces the page which is going to be least likely to be used in the future. But as you can pretty much imagine, it's not possible because we don't know what's going to happen in the future, which pages will be called, which will be in demand. So as we all know, it is impossible to predict the future. So yeah, this scheme is not practical. But still, as this serves as a standard for other algorithms, as this gives the minimum page faults. The second one is least recently used. So what it does, it replaces the page which was not used since the longest time. Okay. It is the same thing as it replaces the very old pages and keeps the new ones. Okay. Old ones which were not used or modified or something like that. So well, this is also hard to implement because for every page there needs to be a timestamp with it. Okay, we need to tag every page with a timestamp of when it was last used. So for every page we need to maintain this data, and so there will be a large overhead for this. Okay, so or we can the another alternative of not maintaining a timestamp is to use a stack of references, but still storing a stack and all this is still very expensive. So the next technique, which is a very simple technique, and we can pretty much guess what's going to happen in this, is first in first out. Okay, it reads the pages in a circular buffer, replaces in round robin style. Don't get confused with the language. It just replaces the page which we fetched first. Okay, so it replaces the page that has been memory with the longest time. It don't it doesn't care whether it was used just recently. If it was fetched a long time ago, it's going to replace no matter what. So that's why it's the wrong approach. So as you can think of, as a process, there are many parts which are running continuously and are heavily used. So they are they are mostly fetched in the start when a process starts. But this scheme will replace it because when it gets old, and there will be a page fault as this was a heavily used portion. So so it will lead to, it can lead to thrashing, as it will going to replace again and again that important part. So it is simple, but as you know, it performs poorly. So you can see, like, these are the pages that there's that are going to be referenced. Okay, this is the optimal policy. So optimal policy, in this we are already given the stream of pages we are going to reference in the future also. So we can implement this optimal policy just for an example basis, but we are not having this stream in practical applications. Okay, so how this optimal policy works? See, two, now the memory is empty, so two is not there, a page fault is generated, two is loaded. Three not there, page fault is generated, three is loaded. Two, it's already there. Now one, empty space is there, page fault generated, one is loaded. Okay, the first time something, a page is loaded, a page fault is generated. Okay, so five is not there, there's going to be a page fault, and the space is not there, we need to replace something. So which one should we replace? The one which we are least likely to use in the future. So we will look into the future this side. Okay, so we have 2, we have 4, we have 3, and we don't have 1. So we will replace 1. Okay, now it's 2, 3, 5. Now 2, which is already there, 4. Now we will look into the future. See, 5 we are going to use next, then 3, then 2 after that. So the furthest in the future is 2. So we replace 2, and so on we go on replacing. Okay, so optimal policy, the best policy, not practical, generates the least page faults, serve as a standard. Okay, the next one is least recently used. Okay, so we load 2, we load 3, 2 is already there, 1 is loaded, now 5. Now we need to replace something. So which one should we replace? So in least recently used, we replace the one which has not been used since the longest time. So we look into the past this time. Okay, so we look into the past and see, 1 is there, 2 is there, 3. So 3 is the oldest. Okay, so we replace 3 and 5 is here now. Now 2 is there, 4. We need to replace something. So we look into the past and 2, 5, 1. So the furthest is 1. So we replace 1 with 4. And we go on like this. So first in, first out is the one which was first will be going to be replaced first. Okay, so we load 2, we load 3, 2 is already there, 1. Okay, now when 5 is there, we need to replace something. So we don't need to look here what happened in the past. We are not concerned what happened with the future. We are just going to look at these, of which was fetched first. So 2 was the first one to be fetched. So we replace 2. Now 5 is here. Now the next one is 2. So, well, this is bad. We actually replaced 2 right now, and we need 2 back again. So you can get how bad this policy is. So 2. Now we need to replace 2, as we know after 2, 3 was fetched. So we replace 3 here and we get 2 now. Now we want to replace 4. After 2, 3, 1 was fetched. So 1 is replaced with 4. Okay, now 5 is there, 3. So now we need to replace 3, as we recently fetched 4, and before that we fetched 2, and before that we got 5. So 5 is the oldest to be fetched. So it is replaced. And so we go on in this manner. Okay. A much better policy is a clock policy. Okay. It kind of combines both FIFO and least recently used. So what it does, it makes use of an additional bit known as a use bit. Okay. So pages are supposed to be arranged in a circular fashion, and when a page is referenced, its use bit is set to 1. Okay. Not at the time it was fetched for the first time, but after that, whenever it is used, it's set to be 1. Okay. So the pointer moves in a circular fashion, pointing at pages each time, and it finds a page with the use bit 0. As soon as that page is found, it is replaced with the new fetched page. And in between, if it passes through a page which has a use bit 1, it complements it to 0. Okay. So we can say the page got saved one time. It was able to avoid replacement because it was recently used. So that's why its use bit was 1. So we can see in this, like, these are the pages arranged in a circular fashion, and this is the present condition. Okay. So our pointer is pointing here. Okay. So its use bit is 1. We can't replace it as it was referenced recently. That's why its use bit is 1. So the pointer moves to the next one and changes its use bit to 0. Now this use bit is also 1. The pointer moves to the next one. Use bit is changed to 0. Now the pointer is here now, and it finds that the use bit is 0. So this page was not referenced recently. So it is going to replace this with whatever the new page is, like this 7 to 7 use bit, and the pointer moves on to the next one. So the pointer stays here until a new page request is there, and the whole scheme is followed again. So next time this page will be replaced if it is not going to be referenced in between, because its base is 0. So yeah, this scheme works in this manner. The pointer moves, change, alternate, complements the ones in between, and changes the first 0 it finds. Okay. And we can modify this policy further by using a modified bit, because the thing is that if we are if a page is loaded and it is modified during the process, and now there comes a time when we need to replace this page. Since this page was modified, so we need to write it back to the secondary memory to save our changes. Okay. We save our changes, so before it is being replaced, it is first written back to the secondary memory. So it should be given some preference over the ones which are not modified. Okay. So now there is another bit added, that is m bit, which is modified bit. So this use bit and modified bit now together make 4 categories. That is not accessed recently and not modified, both 0. Accessed recently, that the use bit is 1, and it was not modified, that is 0. Not accessed, modified, 0 and 1. Accessed, modified, 1 1. Okay, how this policy works is the same clock policy as before. Okay, the pointer points to one position and it scans in the circular fashion looking for U0 M0, that is not accessed recently and not modified. If it finds this page with these two bits as 0, it replaces it. So if it doesn't, now if step 1 fails, it searches for something that was modified, okay, but not accessed recently. So, and in between it changes all the u bits to 0. If it encounters in between any u bit which is 1, it changes it to 0. In the first step it didn't did anything like that. Okay. So it finds a page with this configuration, it replaces it. Now if both of these steps fail, step 3 is that the pointer will be eventually at the start position if these two steps fails. Okay, so it will start again and follow through step 1 and step 2, but this time it will surely find one place to replace, as we have changed the use bit to 0 in between. So it will surely find one of these combinations to replace. Okay, so as we talked before, that modified pages are given preference because they need to be written back to the secondary memory. Okay, so since the cost of replacing a page that is modified is more, and these clock policies, as we saw, are complex and they require a large overhead to do. So there is another technique called page buffering, which is a type of simple first in first out. In this, what happens is that there are two lists. Okay, so one is free page list and the other is a modified page list. So when there is a page which needs to be replaced, and if the page was not modified, so the page is the, the page is put into the free page list. Okay, and the entry from the page table is deleted. Okay, the page is still there at its memory position, just its reference entry in the page table is deleted, and the reference is made into, now it is referenced in the free page table. Okay, free page list. And if the page was modified in between and now it needs to be replaced, its entry from the page table is deleted and it is now entered into the modified page list. Okay, so the free page list consists of a few free frames, and when a new page is to be read, the oldest one get destroyed. Okay, so as I told before, so when an unmodified page is replaced, it remains in the memory and its page frame is added to the tail of the frame. So just it gets entered into the free page list. Okay, and similarly for modified. So this is how free page and modified are handled. So there are advantages of this is that when a, I can say, let's say, by maintaining the free page list and the page replaced is now referred again, so it is easily to get the page back since it is already in the memory and we can just make a reference to it again. And the good thing about modified page list is that since modified pages require to be written back into the secondary memory, so the whole modified list can be written as a bunch in secondary memory than writing them individually. So yeah, in this it is an advantage as they can be written as a bunch in secondary memory. So there is a replacement policy with cache also, as since the memory is increasing and memory increasing, locality is decreasing. See, locality, as we talked before, local references, nearby programs, but and the cache is also increasing. Locality decreases as the modular programming and all the multi-threaded applications. They make references to data which is much farther away. So to counter that, the cache size is also increasing, which is a good news. So if the page that needs to be replaced is found in the cache, means we need a page which is in the cache due to maybe it was recently referenced before. So if we access that thing and the whole cache block which may be containing other pages is lost. So there should be some policy we can employ in that cache also. Okay. So there is a need for a placement policy for buffers. Okay. So mostly the OSs use is the FIFO discipline for cache, which is not so good. There are evidences like the careful page placement policies, that is careful cache management, can significantly means improve your access and references. So careful page management policies can be used to increase performance. That is bringing pages to main memory and minimizing page mem to the same cache slots. So yeah, such a policy is needed, which will minimize the mapping of pages to the same cache block. So if one page is different, the other should not get destroyed.